Welcome. As Android developers, we often focus on adding new features and visual enhancements, but sometimes overlook core issues like performance and quality. Memory leaks are one of the most critical optimization challenges in Android development. In this video, we'll explore what memory leaks are, why they matter, and how to avoid them. Whether you're new to Android or a seasoned developer, understanding memory leaks is essential for building robust, high-quality apps. Let's dive in and learn how to keep your apps running smoothly and efficiently. Memory leaks occur when memory is allocated but never freed, causing the garbage collector to fail and reclaiming unused memory. Initially, this might not seem problematic, but over time, as users continue to interact with your app, memory usage increases. If leaks aren't addressed, your app's memory footprint grows until it crashes with an out-of-memory error. This can lead to poor user experience and negative reviews. Addressing memory leaks early ensures your app remains stable and responsive, even as it scales. Check if your app is leaking memory. Tools like LeakCanary are invaluable. LeakCanary is a popular library that helps developers identify memory leaks in their apps, providing stack traces for easier debugging. Integrating LeakCanary into your project allows you to catch leaks early in development before they impact users. By regularly monitoring your app with LeakCanary, you can maintain high performance and quickly address issues as they arise. Memory leaks in Android often stem from common mistakes. These include failing to unregister broadcast receivers, using static references for activities or views, improper handling of singleton classes, and inner or anonymous class references. Each of these mistakes can prevent the garbage collector from freeing up memory, leading to increased app crashes and degraded performance. Understanding these causes is the first step in preventing leaks. One common scenario is registering a broadcast receiver in an activity but forgetting to unregister it. When the activity is closed, the receiver still holds a reference, preventing garbage collection. This can cause the activity to linger in memory, leading to leaks. Always unregister receivers in onStop or onDestroy to ensure proper cleanup. Register receivers in onStart or onResume for best practices. Declaring views or activities as static variables is a recipe for memory leaks. Static references persist beyond the lifecycle of the activity, preventing the garbage collector from freeing them. This is especially problematic when referencing UI elements like text views or entire activities. Avoid using static variables for views or contexts. Instead, use instance variables and ensure proper lifecycle management. Singleton classes are useful for managing global state, but passing activity context to a singleton can cause leaks. The singleton holds on to the activity, preventing it from being garbage collected. Instead, pass application context to singletons. If you must use activity context, ensure it's set to null when the activity is destroyed. This practice keeps your app memory efficient and leak-free. Inner classes can inadvertently hold references to their outer activity, causing leaks. Avoid creating static variables of inner classes and never pass activity instances directly. Instead, make inner classes static and use weak reference for views or activities. This allows the garbage collector to reclaim memory when needed, preventing leaks and improving app performance. Anonymous classes like inner classes can hold implicit references to their parent activity. This can lead to memory leaks if not handled properly. To fix this, declare anonymous classes as static or use weak reference for any activity or view references. This ensures that the garbage collector can clean up unused objects, keeping your app efficient. Sync tasks are often used for background operations, but they can cause leaks if not managed correctly. Always cancel async tasks when the activity is destroyed. Avoid referencing activity classes inside async tasks unless necessary. If you must, declare the class as static and use weak reference for UI elements. This prevents async tasks from holding onto activities longer than needed. Handlers are commonly used for scheduling tasks, but they can cause leaks if they reference activities. When a handler is instantiated on the main thread, it's tied to the looper's message queue. Messages posted to the queue hold a reference to the handler, which can keep the activity alive. To avoid leaks, declare handler classes as static and use weak reference for activity references. Threads and timer tasks can also cause memory leaks if they hold references to activities. Non-static anonymous classes hold implicit references to their enclosing class. Always close threads in activity onDestroy to avoid leaks. Make sure to manage thread lifecycles carefully and avoid unnecessary references to activities. Timer tasks follow the same principle as threads. If a timer task holds a reference to an activity, it can prevent garbage collection. Always cancel timers in activity onDestroy to avoid leaks. Properly managing timer task lifecycles ensures your app remains efficient and doesn't suffer from unnecessary memory usage. Summarize: always use application context instead of activity context when possible. Never use static variables for views or activity context. Declare classes as static when referencing them inside activities. Unregister broadcast receivers, timers, and cancel async tasks or threads inside onDestroy. Use weak reference for activities or views when needed. Following these practices will help you avoid memory leaks and build stable Android apps. Understanding the difference between application context and activity context is crucial. Application context lives as long as your app does, while activity context is tied to the activity's lifecycle. Passing activity context to long-lived objects can cause leaks. Always prefer application context for singletons and global objects to ensure proper memory management. Static variables persist throughout the app's lifetime, making them risky for holding references to activities or views. This can prevent proper garbage collection and lead to leaks. Instead, use instance variables and manage their lifecycle according to activity or fragment lifecycles. Avoid static references unless absolutely necessary and always clean up after use. Singletons are great for managing global state, but context management is key. Passing activity context to a singleton can cause leaks. Always use application context for singletons. If you must use activity context, ensure it's set to null when the activity is destroyed. This prevents the singleton from holding onto the activity longer than necessary. Inner classes can easily cause leaks if they hold references to their parent activity. Make inner classes static to avoid implicit references. Use weak reference for any activity or view references, allowing the garbage collector to reclaim memory when needed. This approach keeps your app efficient and leak-free. Anonymous classes, like inner classes, can hold implicit references to their parent activity. Declaring them as static or using weak reference for activity or view references ensures proper memory management. This prevents leaks and allows the garbage collector to clean up unused objects efficiently. Async tasks can continue running even after the activity is destroyed, causing leaks. Always cancel async tasks in onDestroy and avoid referencing activity classes inside them. If necessary, declare the class as static and use weak reference for UI elements. This ensures async tasks don't hold onto activities unnecessarily. Handlers can cause leaks if they reference activities. Declare handler classes as static and use weak reference for activity references. This prevents the handler from keeping the activity alive longer than needed, ensuring efficient memory management and preventing leaks. Threads can hold references to activities, causing leaks if not managed properly. Always close threads in activity onDestroy and avoid unnecessary references to activities. Proper lifecycle management ensures threads don't keep activities alive longer than necessary. Timer tasks can cause leaks if they hold references to activities. Always cancel timers in activity onDestroy to ensure proper cleanup. Managing timer task lifecycles carefully prevents leaks and keeps your app efficient. Weak reference is a powerful tool for preventing memory leaks. By using weak reference for activities or views, you allow the garbage collector to reclaim memory when needed. This approach is especially useful for inner and anonymous classes, handlers, and async tasks. Incorporate weak reference into your code to keep your app leak-free. Always unregister broadcast receivers and timers inside the activity. Cancel any async tasks or threads in onDestroy to ensure proper cleanup. This practice prevents lingering references and keeps your app's memory usage in check. Never use static variables to declare views or activity context. Static references persist beyond the activity's lifecycle, preventing proper garbage collection. Use instance variables and manage their lifecycle according to the activity or fragment lifecycle. When referencing classes inside activities, declare them as static. This prevents implicit references to the parent activity, allowing the garbage collector to reclaim memory. Static class declaration is a simple yet effective way to prevent leaks. Always cancel async tasks and threads in onDestroy to prevent leaks. These background tasks can continue running even after the activity is destroyed, holding onto references and preventing garbage collection. Proper cleanup ensures efficient memory usage. Using weak reference for views and activities allows the garbage collector to reclaim memory when needed. This is especially important for inner and anonymous classes, handlers, and async tasks. Weak reference is a key technique for preventing leaks in Android apps. Proper lifecycle management is essential for preventing memory leaks. Always clean up resources in onDestroy and avoid unnecessary references to activities or views. Managing lifecycles carefully ensures your app remains efficient and leak-free. Let's look at an example of cleaning up a broadcast receiver. Always unregister the receiver in onStop or onDestroy to prevent leaks. Register the receiver in onStart or onResume for best practices. This ensures the receiver doesn't hold onto the activity longer than necessary. When using singletons, always pass application context instead of activity context. If you must use activity context, set it to null when the activity is destroyed. This prevents the singleton from holding onto the activity and causing leaks. Make inner classes static to avoid implicit references to the parent activity. Use weak reference for any activity or view references. This approach keeps your app efficient and prevents leaks. Always cancel async tasks in onDestroy and avoid referencing activity classes inside them. If necessary, declare the class as static and use weak reference for UI elements. This ensures async tasks don't hold onto activities unnecessarily. Declare handler classes as static and use weak reference for activity references. This prevents the handler from keeping the activity alive longer than needed, ensuring efficient memory management and preventing leaks. Always close threads in activity onDestroy and avoid unnecessary references to activities. Proper lifecycle management ensures threads don't keep activities alive longer than necessary. Cancel timers in activity onDestroy to ensure proper cleanup. Managing timer task lifecycles carefully prevents leaks and keeps your app efficient. To prevent memory leaks, use application context, avoid static variables for views or activity context, declare classes as static, unregister receivers and timers, cancel async tasks and threads in onDestroy, and use weak reference for activities or views. Following these practices ensures your app remains stable and efficient. Preventing memory leaks is crucial for building high-quality Android apps. Leaks can lead to crashes, poor user experience, and negative reviews. By following best practices and regularly monitoring your app, you can ensure it remains stable and responsive. Tools like LeakCanary make it easy to detect and fix memory leaks. Integrate LeakCanary into your project to catch leaks early and maintain high performance. Regular monitoring helps you address issues before they impact users. Memory leak prevention is an ongoing process. As your app evolves, regularly review your code for potential leaks and update your practices. Staying vigilant ensures your app remains efficient and delivers a great user experience. Many developers learn about memory leaks the hard way after experiencing crashes and performance issues. By understanding common mistakes and best practices, you can avoid these pitfalls and build better apps. Focusing on memory leak prevention is part of optimizing for quality. High-quality apps are stable, efficient, and provide a great user experience. Incorporate leak prevention into your development workflow for best results. Memory leaks can be subtle but devastating for Android apps. By following the 9 proven ways discussed in this video, you can prevent leaks and ensure your app remains stable and efficient. Keep learning, stay vigilant, and happy coding. Thank you for watching. For more information on memory leaks and Android development, check out resources like Medium, Android Pub, and LeakCanary documentation. Stay updated with best practices and continue improving your skills as an Android developer.